Again, welcome everybody. Today I'm going to be covering data structures. So here's the agenda for today. Oh, there you go. So basically, I'm going to introduce why we need to learn data structures in the first place, why people are learning data structures and how they are using it to their benefit, and especially in different situations like coding interviews, or just plain job responsibilities that use this data structures. And then I'm gonna do a brief lesson over the like 8 or so data structures that are seen in interviews and on the job coding. And then I would also have to look at, we will all together, I will do one guided practice together where we could show how a data structure is being used in like one whiteboarding problem. And then for after that, I'll probably give you like 15 to 20 minutes or probably more time to allow you to try and solve a leak code problem. But more on that later. And then I'll conclude my session with my by introducing harder data structures that might not be seen in coding interviews, but there is like, it's never a 0% chance that they might show up. So yeah. So I think this describes this best. I literally got this description from Free Code Camp, basically saying, data structure goes through all the solutions of problems and shows how each problem can be solved by storing specific data into specific formats. Data needs to be more organized. Data needs to be more efficient to sort and search through. So data structures is the best reason why they allow us to uh, think more about what we need to look at. Basically, on the data structures provides a better scope of quote unquote things on the things that we need to look at and the things that whether it be data or things that need to be referenced, all that stuff is really important in the field of data structures and how it relates to bigger coding projects. Now, the motivation. So why learn data structures and their associated algorithms in the first place? Well, coding interviews. Personally, my personal experience, there are many platforms that show, that test their ability to code. There are some platforms that I hate, but there are some platforms I favor. And either way, they show how you can think, basically how you can deconstruct a problem into simpler parts so that you can provide more insight into the processing of data or the processing of what the output is needed for coding interviews. And then second reason to learn data structures is optimization. You guys are about to start your personal projects, which is, lots of components and lots of working parts with each other. I wanted to create this breakout session because I wanted to give you a chance, to step away from those personal projects and see what you can do regarding data structures and how you can manipulate them and see how we got here in the first place. And then finally, the problem solving skills. Again, data structures are better than some others, and some data structures are more efficient to use. Their associated algorithms also provide insight to which data structures are needed to process their data correctly. So especially with the things, especially you've seen it in past whiteboarding problems that you see specific observations or exceptions or patterns or rules or dimensions. These are things that you all noticed when you these are things when you try to come up with, when you try to devise a solution for a certain whiteboarding problem. So with enough practice and enough practice, I cannot accentuate that enough. You may be able to see them more frequently. But let's see. Enough of the chit chat. These are the common data structures that you need to know. And again, I'm gonna go from simplest to like, again, most complex, but again, most frequently used in coding interviews. First one is the basic array. It's the simplest and most widely used data structure. You need to figure out, again, Oh, and I forgot to add this, but I am drawing right now. So let's say I want to draw an array of like 4 elements, and there's a specific, you have to know its basic operations. Insert an element at a given index. So let's say insert at index 1, cool, or insert at index 0, 1, 2, 3. You need to know how to do that. You also need to know how to retrieve it. Saying given an index, you have to figure out what to do there. So, and again, arrays are what I call, give me a second. I call them predefined because unlike other list structures and linked list structures, arrays have a certain size and you cannot change that size. So you have to figure out basically this is the basic structure of how other data structures are built off of. And that third point, commonly asked questions, that takes some good practice. I find these are all easy. Looking at the different ways to manipulate them, as seen with these commonly asked questions, it's a good way to practice with data structures and arrays. So that's I guess a good start if you're still confused on somewhere, I guess. So I'll go to the next data structure. Stacks. This is the reason why undo exists, for a reason. Basically, you store previous states of whatever work that you've created to again, it's limited to a memory, but it shows on it is based on a lethal structure such that whatever comes in first comes out first. So again, if you want to draw it, again, drawing, especially in whiteboard interviews, if the interviewer does give you the chance to draw, then drawing visualizations is the best way to go. So again, let's say you want to stack 3 data elements like 1, 2, 3, saying like, hey, I entered 1 here first, then I entered 2 here first, then I entered 3 here first. Then that's the basic stack. That's the basic stack structure. Again, last in, first out. And what do I mean by that? Those are the basic operations I meant there, like saying I push an element to the top. So let's say I push 4, and then and then I want to then pop 4 because I'm done with that. So I can cross that out, and then I can pop 4, and then again, we return back to our original stack. Those 2 other basic operations is empty. And top shows that, just whether top is like pop, but does not remove the top element. And then it's empty shows, if there's no elements within the stack. Stacks are interesting because they show different ways I want to say they propose different ways of thinking. For example, how can you try to I want somebody to try to answer this. How can you try to use a stack to do the third problem? Check balance parentheses in an expression. Any volunteers?
Can you ask that again, please?
Yeah, so how can you try to use a stack? It's just tell me your thinking. How can you try to use a stack to solve the third problem? Check balance parentheses in an expression. For example, I give you lots of parentheses with random letters inside of it. And how do you make sure that it's balanced? Like there's a correct set of parentheses, if you know what I mean. And by the way, these are parentheses.
So what I would do is I would iterate through the string, and then for every open parentheses, I would add it to a stack. And then every time I get to a closed parentheses, I'd pop the stack. And then towards the end, I would see if like the stack is empty, which means that every opening had a closing.
Yeah, that's true. That's perfect. That's how I would also think of the stack as well. That's a great visualization to see. So again, let me try. Let me try with Michael's visualization. Let's use this weird expression that I made here with the parentheses and ABC. Um, Again, we push a parenthesis every time we see it, and then we pop every time we see a closing parenthesis. So we delete this, and we delete this. And then to add to Michael's observation, we don't care about literally any other characters except for the opening parentheses and the beginning parentheses. So, and then if we can do that last set of parentheses as such right there. So
So how would that work for, like, I get the concept of a stack, but this is just a concept, but it's not actually like a list. We can look at something and we can tell it's a list or an array based on like those brackets. How would that look for like a stack? Is that just like a concept that we use, or is there an actual data type?
let me see. I believe in Python you can just call a stack as such, like stack equals opening closing brackets, I believe. Because the list within Python, I'm going to focus on Python for this duration, by the way. Python is weird with their list such that it inherits a lot of behaviors of many data structures. For example, the stack, it inherits the behaviors of a stack such that you can push it, or in Python syntax, I believe it's append, if I'm not wrong. And then, yeah, it can also do pop, and then sort of similar ways. So Maya kinda yes, but put an asterisk near that yes, because I'm not sure of the I guess fully fleshed out syntax of Python. So yeah.
Okay. It sounds like it's just a list and they give you kind of your limits for how to
Kinda,
treat it
yeah.
like a stack.
Yeah, definitely. Yeah. Uh so yeah, that's all I have for stack. Again, it's last in, first out. Again, whatever enters in most recently is the one that exits most recently. So that's the main key takeaway of stack. All right. Next one, queues. As the literally the name implies, think of it as a line. So let's say let's just deal with different numbers. 4, 5, 6, 7. Yeah. Let's see. Queues are weird because there's no good way to visualize them. Again, I'm drawing a rectangle. That might not work for you, but it might work for, or it might look like as a line, or it might work as something else for you. But for me, it works best as a rectangle, as a disclaimer. So let's say if you want to include 4 data elements such that, 4 entered first, then 5 entered next, then 6, then 7. Oh, sorry. The other way. It's a line. So literally a perfect real life example of a queue, a line of people waiting at a ticket booth. If a new person comes, they will join the line from the end, not from the start. And the person standing in the front will be the first to get the ticket and hence leave the line. So let's say Forrest. Oh my gosh, thank you, Terrence. I just realized my mistake. It's first in, first out.
Yeah,
Like
no
a pest
problem, man.
dispenser. Yeah, Maya, correct. Thank you for that. I will change that. I will edit that after this session. Sorry, you're correct. First. So again, this is the front. This is the back. No, Maya. Maya literally put it correctly. It's literally a pest dispenser. So let's say you have an empty pest dispenser, and I also if you don't know what these are, basically they're little candies that just imagine them as little candies in a long rectangular tube. Let's imagine that you had an empty pest dispenser like such, and you want to fill that pest dispenser with candy. So you fill it up. The first, what you would consider the front, is the top of that pest dispenser. Front. And then what you consider the back of that pest dispenser is the bottom, the most deepest candy. Basically, in queue means to insert an element at the end of the queue, which means the back. Now I had to unfortunately manipulate the pest dimension, because how can you enter a candy from the way bottom? It sounds weird, right? That's why a line sounds best here. And whether we're waiting for a ticket or going to the bathroom, you always have to start at the end of the line. So that's what basically NQ means. You're inserting yourself at the end of the queue. And then when you DQ, that's when you in the front. That's when you remove yourself from the front and do whatever processing you need to do. So yeah. Again, just like stack, you can do also is empty, or also you return the first element of the queue. Yeah, basically pest is first in, first out. Yeah. And then again, commonly asked questions that you can see with queues. Apparently, you can implement a stack with this. Now, it takes some thinking, because how can you do that? It's a stack is last in, first out, while a queue is first in, first out. How can you do that? I will give you time after I introduce the data structures to figure that out as an independent problem. So yeah. Unfortunately, I'm not as experienced as queues as with the other data structures I'm going to cover. So if you want to learn more about queues later on, and I'll explain why I'm saying this, feel free to hit me up. So yeah. All right, next data structure, linked lists. Think of it as an array, but with a major difference. Memory is not in sequential order. Like again, an array is basically items in order. And to go into a little bit of our computer architecture, arrays are built such that their things inside are one after another. So let's say 1, 2, 3, 4. That 1 is located in the memory before the 2, and that 2 is located in the memory before the 3, like in a sequential order. In linked list, they could be anywhere and everywhere the memory allows, because linked lists have node, and a node contains two important things. It's data. So let's say I don't know. Let's say since it's August, I'll use 8. And then a pointer to its next node, or so let's say it points to here, to this next to this new node, and then I'll just say 7, and then points to another one. Then this says 6, and then it goes another one to point to another. Sorry for my bad handwriting or bad drawing skills, but you can see how I am building the linked list as such to visualize how linked lists are not sequential, like how the memory is not sequential in order. There are a lot of basic operations, but you need to make sure, again, a linked list is a chain of nodes where each node contains information like data and a pointer to the succeeding node in the chain. Let's see. Linked list, is the data always Maya asked, is the data always numeric, or can it be letters, words, etc.? It could be anything. Data could be anything. Answer, yes. And I believe several weeks ago, you guys have covered like for a single day, you did like a data structures introduction. Yes, actually, okay, I'll come back to that. But linked lists are used to implement file systems, hash tables, which I'll cover later on, and adjacency lists, and again, which I'll cover later on. And yes, Maya is correct. It is kind of used in a weird blockchain methodology. It is the core of how blockchain works, but blockchain, I guess, modifies it in a weirder way. And I'm not fully experienced in blockchain to fully speak on it. So yeah. But if I remember correctly, this is the only linked list that you guys covered in that data structure today several weeks ago. This is what you call a singly linked list, where it's unidirectional. It only goes one way. You only know the reference to the next node. Well, what if, I'm sorry, I have to delete this. But what if I can show you a different type of linked list? And just like a singly linked list, this linked list is also covered as well. This is called a doubly linked list. Sorry, a doubly linked list, where it's bidirectional, where you still have the data, you still have the, excuse me, give me 1 second. You still have the reference to the next node, but the key addition here is that now you actually have a reference to the previous node. So something kind of like this, and my bad drawing skills is going to be the vein of me. 3. Oh, that's not where I put it. It's kind of weird because now you have to, it's weird now because you have to keep now reference to all the pointers that you're dealing with. In addition to the previously, well, sorry. What I was about to say is that compared to the singly list where you're just only referencing the next node, now you have to consider, oh, these nodes now can reference each other because of how they reference their ancestor and their successor. So again, I can do such as like this. I can't draw for life, or like that. Yeah, something like this. And be careful, because I just did a grave mistake here. Oh, well, it might not be a grave mistake, but it depends on how you looked at. This is the minute observations with linked list. It's the annoyance of their pointers. Again, you have to be considerate of like what each pointer is pointing to. And Maya asked, would that be considered like a loop in the commonly asked questions? Yeah, kinda. In a way, it's weird because again, all pointers point somewhere. If you figured out that the pointers point to a previously referenced node that you already processed, then again, you can detect a loop, or you can try to figure out something regarding that, do some output with that stuff. So doubly linked list doubles the work of the singly linked list by now referencing not just the next node, but also the previous node. So yeah. I am halfway through my data structures. Does anybody have any questions so far about arrays, stacks, queues, or linked lists?
Do you have any examples of questions that you've solved with these?
Yes, I will actually after I introduce the latter half of my data structures, I will actually do one for you guys. That I actually I had a coding interview yesterday and I was asked this question. So yes, I will show you one. So any more questions? All right, I'll move on to the next. I'll move on to the next set of data structures, which are graphs. Think of it as a set of nodes that are, just think of points that are connected to each other. Think of it as like a network from one thing to another, from one thing to the next. So, and you might be thinking, why are they called graphs? I don't know. They're like that because you can, let's say you have lots of points somewhere. Again, it's like a network, like it has a network-like system. So, I have all these points here. They have random data in it. And there are actually two types of graph. The first graph I will show you is an undirected graph. Basically, as it shows, they're just connected. They're not directed, so they can be. The weird thing about graphs is that they don't have to follow a set of rules. They can be connected however they want. They can be connected however the original programmer designed it to be. So I can code it like that. I can code it like this, or connect it like that. Boom, that's a graph right there. Or I can add an edge. I can add an edge right there. Boom, that's another graph right there. In typical graph fashion, we call these nodes with these data in it vertices, and then we call these connections from one node to the next edges. And what you saw, what I saw right now, is an undirected graph where, again, they're just connected, plainly. But what if let's say I wanted to show you a directed graph? Well, basically, it actually shows direction. So now we can actually draw arrows on some of them to indicate that that data transfers properly from one node to the next. So yeah, like that, like that, like that. So yes, and then there are many in a programming language. There are different ways that graphs can be represented. For example, we can use, if you guys took some form of algebra, you guys probably remember like a matrix. Well, we can use the dimensions of a matrix to show which vertices are connected and which aren't. So for the sake of being simple, I will show, let's focus on 1, 2, and 3 first. And then I'll show how the matrix is formed. 1, 2, 3, 1, 2, 3. You can, so if the main rule of adjacency matrices is that what the vertex on one dimension is connected to the vertex of another dimension via a 1. If it's not connected, then 0. For example, let's first look at how 1 is connected to 1. Well, there's no edge that connects 1 to 1, so it's 0. Same thing with 2, same thing with 3. But we do see 2 is connected to 1. And we can, 2 is connected to 1, and then 1 is also connected to 2. And then we can also see that 2 is connected to 3. And same thing otherwise, that 3 is connected to 2. The only connection that we don't see is 3 and 1, and 1 and 3. So that's what an adjacency matrix looks like. It shows which vertices are connected via matrix and math. And then the second way to show this in a programming language, and I say, oh, before I go on to the second one, matrices again can be represented by 2D arrays, right? So take note of that as you try to look at graphs. And then adjacency lists, as it says, you literally list down the vertices and then the edges that they're, and I guess you can, I don't know what you would put here. I guess you would say partners, I guess. Or connected to. Yeah, that's what I connected to. Yeah. See, 1 is connected to 2, 2 is connected to 1 and 3, 3 is connected to 2. That's the basic format of an adjacency list. And again, in Python, I believe lists are with open brackets, close brackets, so that's how you can look at lists. Regarding breadth and depth first search, I will cover that later on. If you do plan to do that as an independent like practice problem, then I will be able to help you because they're kind of hard, they're kind of difficult to understand if you don't know, if you can't really work with graphs yet. So yeah. I'll go on to the next data structure, which is trees. Basically like a graph, but cycles cannot exist in a tree. And when I mean cycles, basically, again, it cannot go around. It cannot go around in a circle such that if you find a path from the original vertex to the same original vertex, then that's impossible to find. Trees are kind of, again, trees are like branches because again, there's always the top of the tree, right? And they always have these branches that always, by the way, these are how trees are formally visualized, that they always have their smaller branches. In trees, we call them children, so that they bring down to more ancestors and more ancestors. So like this, something like that, such that give me a second. Such that it comes from the top down. That's basically the formality of a tree. And there are many types of trees, as you can see here, but the most common trees that I see most frequently are binary trees and binary search trees. And basically a binary tree is you have a node and it has 2 children. In other words, it goes downwards to 2 other nodes. Same thing with a binary search tree, but binary search trees are ordered. And let me show an example real quick. Binary tree, let's do it like this. I'll just take random numbers I'm thinking of right now. 11, 3, 2, 1, 6, 9, 4. That, again, that's a typical binary tree. It just goes from 1 node to its children of 2 nodes. Or it could caveat, it could also have less than 2 children. It could technically also have 1 children or no children at all. Now what a binary search tree is, now it's like a binary tree, but the values are now actually ordered. So for example, let's see. Let me delete all of this again. Oops. Let's say you want to let's look at an example that I'm looking at. Let's put 10 here, 7 here, 15 here, 6 here, 8 here, 14 here, and then just, I don't know, 30. As you can see, the left child of a node is always smaller than its parent. And then the right child of its parent node is always bigger than its parent node. So it's basically like ordering okay, by the way, I'm only using numbers. The same rules apply with alphabet, alphabetically, or strings with some other lexicographical order. This is a binary search tree where, again, you can take a look at how they're ordered and see how their right node is always bigger and that their left node, or sorry, their right child is bigger and that their left child is bigger or smaller. Again, those are some commonly asked questions regarding trees. A height of a binary tree is basically this, like how many levels is it? And then there are, if you're not side note, if you're not comfortable with recursion yet, then trees may be difficult to, especially in coding interviews, trees may be difficult to understand, but with more practice, trees become more easy to see that, oh, that's how trees are processed. So yeah. I'll go on to the next data structure. Okay. They're pronounced as tries. I don't know why the CS community says that way. I agree, but it's kind of weird. Tries are interesting because they show that also known as prefix trees. Also known as prefix trees. They're tree-like data structures that prove quite efficient for like solving problems related to strings. It provides fast retrieval and it's mostly used for searching words in a dictionary, providing, the reason why Google and Bing and Yahoo have auto suggestions in their search engine, and even for like IP routing. So for example, let's consider these 3 words: top, thus, and there. Let's see. Let me actually just write it out so I can visualize. You can see how trees are formed. So we can see that we can make top like this, just by processing each character. And then, give me a second. We always, in typical trees, they always mark a node with some true or false value or some other binary value to say that, hey, this is the end of the word, and that this path from the bottom to this bottom node means that it's a word. So with that top, let's try thus now. And then there, we already have a T, we already have an H. We can just simply make another path to make an EIR. And then I forgot to, how do I say this? Mark the end of the word. If you have lots of similar words that have similar spelling, then you might not have a lot of branches. But if you have like unique words that have different types of spelling or don't follow the rest of the words in a list, then it might have lots of branches. Again, the words are stored in the top to the mana in the top to the bottom manner, where the green starred nodes P, S, and R indicates the top end of top, thus, and there, respectively. And then those are some commonly asked questions regarding how do I say this? Tries, including printing all of the words that you see, or counting the number of words that you see, or apparently you can sort an array with a try. I've never done it myself, but I've seen interesting solutions on how tries can be used. And then last but not least, hash tables and hash sets. So to give context, hashing is a process basically to like identify objects and store them at some pre-calculated index that we call a key. These objects are stored in the form of a key value pair, and they can be stored in such a item is called a dictionary. And each object can be searched using that key. And it depends, and the performance of these hash tables and hash sets depend on the function itself, like the hashing process that it actually takes to process things into their hash version, the size of how big these tables are, and collision handling. And collision handling is basically a way to prevent two objects having the same hash value. The best way to visualize this, unfortunately, basically, so here's an illustration of, so there's no best way, unfortunately, to visualize hash tables and hash sets because they can take in many different fashions. But let's say, you're at index 3, and this is 16 and 17 for some purpose. Let's say the hashing function hashes the index. So there's this 3 that turns this 3 into a unique key. I don't know, it could be some random combination of digits and letters and other characters to uniquely identify itself. And it can be stored as a data. So think of it as a glorified array or glorified data structure, but a way to encode its original data or original key, original input value to uniquely store more other values, unique other values. So for example, if again, you input a 16 unique key and then keep its original data, input 17 unique key, unique data. Is this the same type of hashing we talked about for passwords? Kinda, yeah. Yes, especially in the world of cybersecurity and cracking passwords and breaking up the defense systems of many protected systems. Hashing is hashing is the way to encode it. Many cybersecurity people try to decode it through many algorithms and processes. So yeah. And then those are the commonly asked questions regarding again, those hash tables and hash sets can be used in any situation. Like there's a running joke within the CS community that if you get stuck on a problem, just say hash map or hash table or hash set, because the technical recruiter will be instantly impressed by that. But in real life advice, don't do that because that sounds weird. Those are some commonly asked questions regarding hash tables and hash sets. And again, they're more used with arrays because again, they're like kind of glorified arrays. And yeah, those are all the data structures that I have. Does anybody have any questions before I go on to an example that I plan to do? Going once, going twice. All right, I'll go on now to basically guided practice. I forgot to delete that caption, but now we're gonna get started on, try to implement, you, again, everybody in here has different experience with different types of data structures. So, my best piece of advice is to start working on the ones that you're least confident about, and start, maybe get some refreshment on the ones that you're most comfortable with. So I'm gonna get started with an example. I was literally asked this question literally yesterday in a coding interview. Basically, I have to write an algorithm to determine if a number is happy. Basically, and that's the definition of a happy number. Start with any positive integer. So n is greater than 0. Replace the number by the sum of the squares of its digits, and then repeat the process until the number equals 1. Or it loops endlessly in a cycle, which does not include 1. If it ends in 1, it's happy. So let's see. How will we get started with this question? Well, a good way to get started with this question, with a question like this, is, okay, so I'm about to start the question. So make sure to take the mental processes of how certain problems are solved like this. So yeah. So a good way to get started with a question like this is to make a couple of examples. Let's start with the number 7. Cool. The next number of it will be 7 squared, which is 49. Now, the next one will be the sum of the squares of its digits. So 4 squared plus 9 squared, which is 16 plus 81 equals 97. All right, 97. 81 plus 49. I need a calculator. 81 plus 49 is 130. Cool. Okay, 130. 1 squared plus 3 squared plus 0 squared. 1 squared plus 1 plus 9 is 10. All right. And then 1 squared plus 0 squared is just 1. So, all right, cool. We can clearly see that if we continually repeat the process of squaring, then adding the digits, we get to 1. Because we got to 1, we know that 7 is happy, and we should show it's true. But let's start with another example. I have another example here, 116. So let's see. Give me a second. All right, 116. 1 plus. Okay, so I'm about to speed up the process a bit so that you can see the patterns that we're about to see. 1 plus 1 plus 36, 38. 9 plus 64, 73. 49 plus 9 is 58. 25 plus 64 is 89. 64 plus 81 is 145. 1 plus 16 plus 25 is 42. 16 plus 4 is 20. 2 squared is 4. 4 squared is 16. 1 plus 36 is 37. Oh, but wait, look at this. 9 plus 49. I feel like we already had that number before. 9 plus 49 is 58. We've entered a loop. So by repeatedly applying the square and adding process, we eventually get to 58 again. And because we are back at a number we've already seen, we know that there's a cycle, and therefore it's impossible to ever reach one. So for 116, this should return false. Yeah, false. So Okay, so based on our exploration so far, we can see this ending up three ways. One, it ends back at 1, as with 7. 2, it gets stuck in a cycle, as we'd see with 116. Or 3, it keeps going up higher and higher and higher up towards infinity. Now, for that third option, it keeps going higher and higher. It sounds really annoying to detect and handle. Like, for example, I don't have enough space for this. Please excuse my erasing for all of my work. In a real interview, you wouldn't erase all your work. But that third option sounds really annoying to detect and handle. How can you detect numbers that are going higher and higher and higher? And how would we even know that it's going to continue up rather than going eventually back down, possibly to 1? Well, looks like we don't have to worry about it. Let's consider a 13-digit 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 nines. The next, if you apply the same process of squaring each of the digits and adding them all up together, for example, with this 13-digit 9, you get 1053. And then it looks like it went way down really smaller. So again, and then we can try to apply this to, I don't know why I chose 13 digits, but I can show you with 1-digit 9, 2-digit 9, or sorry, I keep saying 2-digit, 3-digit because I don't want to say its full number full name. Like, what is this? I don't even know. That. This next number is 81. This next number is 162. This next number is 243. Next number is 324. So for a number with 3 digits, it's impossible for it to ever go larger than 243. That means it will have to either get stuck in a cycle below 243 or go down to 1. Numbers with 4 or more digits will always lose a digit at each step until they are down to 3 digits. So we know that at worst, the algorithm might cycle around all the numbers under 243 and then go back to 1 it's already been to, whether it be a cycle or back to the number 1. This confirms that it won't go on indefinitely, allowing us to kill that third option of going infinitely higher and higher. So that just does it. We figured out the problem. There are now 2 parts of its algorithm. First, what's its next number? Next number. And no, the second part is, are we in a chain? Are we in a chain, or have we reached 1? Have we reached 1? Part 1 can be done by using the division and modulus operators to repeatedly how do I say this? To repeatedly, I can't English. To repeatedly take digits off the number until none remain, and then squaring each removed digit and adding them together. Then part 2, we can use one of the data structures that I called, that I recently taught, which is a hash set, because each time we generate the next number in the chain, we can check if it's already in our hash set. If it's not in the hash set, we should add the number in the hash set. If it is, that means, oh shoot, we've already reached the cycle and it should return false. The reason why we're not using a list or array is because we're repeatedly checking whether or not numbers are in it. Checking if a number in a hash set takes O of hash set takes O of 1 time, whereas for an array it would take the minute observation of arrays is that you have to process the whole array to see if it's in an element, or if you see if the element is specifically within an array, which would take O of n time. And coding interviewers like that optimization, so hash set is the way to go. So after coding this, and after explaining your thinking process, and after showing how you would go about solving this problem, this is when you would get started. And again, I apologize for removing all my work, because I actually need to write the code. All right. So let's just define a function. Oh, and let's just say that the function is happy, and then you're given an n. I'll define another function within it, saying that basically this is the get next number method, where basically we would again get the total sum of the current. We would start initialize it at 0, because we're trying to add all the squares of the digits. And then while n is greater than 0, so while n has digits to process, there is a unique function within Python called diffmod that basically gets something like this. Hold on, let me write it out. It basically takes the modulus, or the remainder. It basically takes outputs to outputs, where n is the new number to process, and then digit is the remainder. So let's say 324. The new n would be 32, and then the digit will be 4. In this situation, because we're modulus by 10, we're modding it by 10. That's what diffmod does. It basically gets the division and answer together. And then within total sum, that's when we would add the square root of the digit. And then you return the total sum. Total sum, yes. All right. And then, all right, now you have this function, but you're not actually returning anything yet. Good point. Let me actually try to, I have no space for it, so let me, give me a second. Excuse my, I wish I had more space, but let's try, oh, dang, I have no space. Okay. Oops. Oops. Oops.
So wouldn't, and maybe I misunderstood a step, wouldn't the div mod just give you like that example that you did? What was it, like 346 or something? Let's say 6. Wouldn't it just give you 6? It's not going to break out all 3 of them, right? Or am I missing something?
So let's say you input 6, right? The 6. Well, n would be 0, and then the digit would be 6. It does do 2 outputs, but once we reach, how do I say this? That point to where we can't process any more digits, that's when the while loop exits. Do you understand, Maya?
I mean, not really, because when I'm looking at this, like if we're supposed to be doing the square of all 3 numbers, right? So where do those first 2 digits get squared for us to get the sum?
Oh, I see your concern. So like how does the 3-digit actually, okay, actually that's a good idea. Let me go through this. Or that's a good question, because especially the interviewer will ask questions like that. Let's go with the number 324, the same number that I proposed. Div mod, when you apply div mod to 324 modulus 10, it will get n at the new n will be 32, and the digit would be 4. Then, now that we know the digit is 4, we square 4. We square that digit. 4 times 4 is 16, and add that to the total sum. So the total sum right now is 16. Then we do it again. We know that our n is 32. So
Oh, and that's where the while loop comes in.
yes, and
Oh,
32.
okay.
32, so 3 and 3 and 2. 2 times 2 is 4. And then we look at again at our n. Oh, n is still greater than 0. 3, it's 0 and 3. Because there's only a remainder. There's no other way to get 10 out of 3. So, and then 3 times 3, it's 9. And then adding all of that up, that's 29. Do you understand, Maya?
Yes.
All right, cool. All right, now that we have our function, in our way, I don't know if I can move this. I hate PowerPoint. But now we can return back to the isHappy function. Oh my gosh. We can return back to the isHappy function and create a hash set. I believe, so for reference, this is the tab so that you can you can keep reference of like where the tabs are, so that I'm just moving it onto the side because I have no other space for this. So we can now declare a hash set, and in Python, I believe you can do this. That's it, hash set. That's many of the, again, as I previously mentioned, lots of the things in Python like a dictionary and a set inherit a lot of the behaviors that I previously mentioned. And unfortunately, I'm more experienced in like Java and stuff. So maybe it's a good way to, explore how to see how Python is really taking that vantage point of that stuff and why people like it a lot. So, and then, okay, so we declared a hash set. And then let's do this while we see n is not equal to 1 and n is not in scene. We can say that we can add that number to our set, scene.add n, and then get the next number of it by just reinitializing it. N equals get next n. And then finally, after, if either n equals 1, or if you see, no, so to exit this while loop, we have to either see that n equals 1 or n is in the scene hash set. Basically, to finish off the function, you would just say, hey, tell me if n is equal to 1. Because that will return true, because again, happy numbers have to end at 1 after all that summing of square root of digits. And if it doesn't, well, it will return false. And then one more thing, lots of coding interviewers like to ask complexity analysis, so like the time complexity and the space complexity. Time complexity for this problem is kind of hard. It's actually challenging. We can just look at actually, for my interviewer, he recognized that the whole, if you consider both the definition and the code after that, it's actually hard to see the time complexity. So he was lenient enough to actually just say, hey, okay, so what's the time complexity of get next? And I explained to him that the time complexity of get next is log of n, because finding the next value for a given number has a cost of O log n due to us processing each digit in the number. And the number of digits in the number is usually given by log of n, surprisingly. And then for space complexity, it's also O log of n, because it's a measure of what numbers we're putting into the hash set and how big they are. And if you put in gigantic numbers, so for space complexity, it would reach O of n if it's big enough to, like, take a lot of space in the hash set. But yeah, that's a solved problem. Does anybody have any more questions or issues or concerns about how I approach this problem or anything regarding this problem?
I just have one question. I just want to make sure I'm not missing anything. So on
Sure.
here, it looks like it was just assumed and not written out that we just push the total sum to scene.
Yes.
Okay, I just want to make
And
sure.
unfortunately, if I had more space, I would show the proper indentation. But I also drew those dashed lines to show the indentations to say that scene is properly on the same indentation level as the definition of get next. The while loop is on the same, the while line specifically is on the same indentation as get next, the definition of get next.
I just wanted to make sure. I feel like between you all, the TAs and the instructors, you all are always doing something in your code that is more simplified than how I would approach it. So I just want to make sure I didn't miss anything.
Yeah, definitely. And context, all us TAs and instructors come from different walks of life, and we all have different experiences. For example, when I was taught this in my data structures class, it was Java, and Java is still the standard because of AP classes and all that stuff. How do I say this? So when I had to learn the Python and the inherent behavior of Python, it was kind of weird because it became more simplified, and I wasn't just used to that. So yeah, thinking in different languages is also good for you and stuff. So yeah. Any more questions? Oh yes, I saw your question, Logan. Let's see. Could a dictionary also work? I could see why not. Yeah. Dictionary. Yes, but I think it has the same implications of hash set, and it goes the same either way. So yeah. Now, I'll leave this as a challenge to you all, but there is a way to do this via an quote unquote implicit linked list. And implicit means we don't actually have actual linked nodes and pointers, but it still takes on a linked list structure. If you can try to figure that out and see how that works out, come talk to me. I would like to hear your solution. But now is the time for it's your turn. I will actually put where is it? I lost it. I've compiled lots of leak code questions that take on manipulating the data structures that I've mentioned in my session today. I had 247 and let's see, Rafael still wants to fix a bug. So I'll give you until, oh, sorry, let me put it in chat, sorry. If you click on the list, sorry, if you click on the link, There are many problems that I've done that I practiced with before and seen solutions for, and you need access. What are you talking about? You clearly can access it. What are you talking about? You can clearly access it. Anyway, sorry for my mistake. I want you to tackle one problem that you guys find fit, whether it be one that you're most comfortable with or something that you're not comfortable with. And if you're taking on a problem that you're not comfortable with, that's amazing because you're trying to learn more about this data structure for yourself. And I believe on Wednesday we have another whiteboarding session by Ben. So it depends on the problem that he chooses for his whiteboarding session. It'll be great. So yeah. So it's currently 2:49. I'll give you all. Adam, is it okay if I give them 15 minutes to independently try and tackle a leak code problem of their choosing, and try to let them share the results afterwards?
Let's check in real quick. I apologize. I've had to be in and out. How is everyone doing? And when did we last have a break, first of all?
So I did not take any breaks, to be honest. I was not considerate that. I apologize.
No worries.
And I see Michael's concern. If you can't understand the problem in 15 minutes, that's okay. If you can try to pseudocode your solution, then that would be perfect because at least you're thinking about the design of your problem. So, Adam, I just proposed them tackling a leak code problem for 15 minutes, and then after those 15 minutes, I plan to call on like 1 or 2 students about their experience about their independent practice, and then afterwards I conclude. Is that okay?
I think, let me check in with Rafael real quick.
Okay.
My only concern, Gerardo, is just time. Actually, why don't we do this? Both because I think it's a good time to take a break because it's been just a little over an hour. And also because I think if we try to do the leak code problem now, we're just going to end up not giving it the attention that it deserves because I know Rafael wanted to wrap up some stuff and that we want to give folks some time to work on stuff in the afternoon. How would everyone feel about setting aside some time and then we can have maybe 30 to 45 minutes later in the week to look at the leak code problem? Gerardo, I know that's a bit of an ask for you because you've led your breakout session, but how does that sound and would you be down for that?
Yeah, I will be down for that. Yeah, I will be down for that. Yeah.
Okay.
So, can you
Awesome.
reiterate your plan again? Because
yeah,
I have one more slide. I just want to conclude. If we're gonna skip the leak code.
For sure. Yeah, we're gonna skip the leak code for today.
Okay.
Maybe I'll check in and see what Ben is going on. Maybe we'll kind of even do a little bit of a combination if he's going to be doing some whiteboarding on Wednesday.
Okay.
But probably later this week, we'll have another afternoon optional breakout session where we can reconvene and you can share the problem and folks can work on it and then we can review it and have the time we need to dig into it.
Okay, I'm okay with that plan. Yeah, definitely.
Awesome. Thank you.
So yeah, let me just conclude by saying this. Yeah, data structures is difficult. As Michael said in the chat, that's why many interviews are as long as they need, like 1 hour, 2 hours. They are difficult to understand. But as in the second point, practice, 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 practice is your baby. Practice helps you a lot so that you can understand how, again, the minute differences, the observations, the syntax, all the things that you can see within a certain data structure coding interview problem will help you. Now, I only showed the data structures, what most coding assessments would test today, but unfortunately, these are some topics that I've heard from my personal friends and some Reddit posts that there are some coding interview questions like this, like dynamic programming, heap, priority queues, recursive backtracking, and other weird sorting algorithms that I don't even know of. If you would like to explore them and see how they're useful, especially with dynamic programming, heaps, yeah, all of them, go ahead. And if you find any observations that you find really interesting, don't feel free to share them with, in Romeo or with me or any other TAs. But other than that, that's all I have to present. And yeah, thank you for listening.
Gerardo, that was awesome. Thank you. I think this is going to be a really good resource for people as we continue preparing for interviews and things like that. So thank you very much, man. Much appreciated.